All right. The traversals is what we were like talking about. And the reason they're important is because, well, what comes after A? Like, what's the first thing in this tree? How do I traverse this? When it's a linked structure, it's easy. That's when it's a singly linked structure. You start at the head, and then you go to the next, and you go to the next, and you go to the next. With trees, not so simple. So we're going to talk about three main traversals and another one. Preorder, Inorder, Postorder, and level order. Pre, in, and post are remarkably similar. So here's the idea with preorder. Preorder is, okay, you always start with the root. So you look at the root of the whole tree, okay, and you say, okay, we're going to deal with this node first. In our case, dealing with the node is just going to be printing out the data because we're not doing anything other than just traversing it. So visit the first node, get its data, and print it out. Then do another preorder traversal, but on the left subtree. And then once that's done, do a preorder traversal on the right subtree. And then when that's done, we're done. And if you're like, well, yeah, you're skipping steps here. You're just saying, oh, do a preorder. No, it's recursion. That's exactly what we want it to be. So we start by saying, okay, do preorder on this one. So we print out A. Great, we're done that. Now we go to the left and do a preorder traversal. Oh, okay, so B is the root. Visit B, then do a preorder traversal on the left. Okay, great. Visit D, now go to the left. Oh, there's nothing. So D comes first, then H, before we get back to E. Okay, so we visit left, right. Okay, we visit before the other recursion calls, the other recursion calls. And then there's the Inorder, which is a slight variation. The Inorder traversal is do Inorder on the left. Once all of that's done, visit the current node, then do an Inorder on the right. So if we take this, let's open up Paint. Okay, and okay, great. So we start at A, but we don't do anything with A until we're done dealing with A's left subtree. So we go to the left subtree. But we don't do anything, we go to the left subtree. We don't do anything, we go to the left subtree. Well, there's nothing there, so we're done with D's left subtree. We visit D. Then we go to the right subtree. Don't do anything yet. Okay, wait here, I'm here now. We go to H's left subtree, nothing there. We print out H. H's right subtree, nothing there, we're done. Go back to D, go back to B. Now we're done B's left subtree, so print it out, B. Then go to the right, go to the left, nothing there, print out E. I'm drawing with a mouse, so don't judge me. Go to the right, nothing there, return, done. Now we finished A's left subtree. We finished the Inorder traversal on the left subtree, so now I can print out A. We go here, go left, go left, go left, nothing there, go back, I. Go to the right, nothing there, go back up to the F. We finished F's left subtree, so we can print out F. Go to F's right, nothing there, go back to C. We finished all of C's left subtree. Then go to, print it out C, go to the right, go to the left, nothing there, okay, and then G. Right, done, 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 done. Yay. Right? So, of course, the Inorder traversal is D, H, E, B, E, A, I, F, C, G. Left, visit, right. So the in order, we visit in between the recursive calls. So seeing the preorder, where we access the data before recursion calls, and then the in order, we do it in between. Who wants to take a wild guess what post order would look like? You don't have to tell me the string. Tell me where this access the data, access the root stuff. Where is it going to be relative to the other two recursive calls? Someone put in the chat. After post. Exactly. Computer scientists are not clever enough to come up with fancy names. We just use intuitive names, which is fantastic. So let's see if I can, okay, let's double check this. I have DHBE, AIFCG, AIFCG. Yeah, I did it right. Okay, now post order. Okay. Let's try this. Let's see if I can do this one. This one tends to, I don't know. This is the one that people tend to mix up just because it does feel a little weird. Okay, I'm going to move it there. So now we go to the left, we finish the left, we go to the right, we finish the right, then I can visit. Meaning A should be the last thing. Because I have to do all of A's left, then all of A's right, and then I can print out A. So let's see. Okay, we go to the left, go to the left, go to the left, nothing there. Go to the right, go to the left, nothing there. Go to the right, nothing there. I can finally print out H. Then we return to D. We finish D's right subtree, so we can go back to D. Okay, we go back to B. Well, now we need the right subtree. Go there, go left, nothing there. Go to the right, nothing there. We can print out E. Return to B. We can print out B. We can go back to A. Great, we finished A's left subtree. Now we go to the right. So we go here, there, nothing there, nothing there. I. Go back here, nothing there. F. Go back, go to G, go to the left, nothing there. Go to the right, nothing there. Then we go to C. We're done. Then we go to A. We're done. Let's see if I got this right. HDEBI. HDEBI, FGCA, FGCA. Awesome. I did it. So that's the post order. So pre would be A, then left, then right. In order is left, then A, then right, where A is the data in some root node. And then post is left, right, and then visit A. Cool. So those are traversals. And then last, we have level order. Now, technically with level order, we could do it recursively. But it's not as nice and clean as these are. I mean, the recursive in order is here. Let's see if I can go where, no, that's, come on. Here we go. What am I looking for? Something with a tree. Let's see, tree. Perfect. Okay, here's a tree. Come on, they got to be in here somewhere. Preorder. Here we go. Here's the recursive. Here is the function preorder. Okay. If current's not null, do something with the data, then do preorder on the left, then preorder on the right. In order. If current's not null, in order on the left, do something with the data, in order on the right. Post order, if current's not null, do post order on the left, post order on the right, and then deal with the current one. That's it. Now, level order is a little different, but it's actually really simple to implement. So the idea with level order is you go down by the level, left to right. So I would say, okay, A, B, C, D, E, F, G, H, I. That would be level order. You go down, here, do I have an example? Yeah. A, B, C, D, E, F, G, H, I. You go down, starting at the top, you read left to right, A, B, C, D, E, F, G, H, I. And the easiest way to do this is with a queue. So go with me on this. You start with the queue, you enqueue the first element. Okay, great. A is there. Then I create a loop that says, well, my queue is not empty. Dequeue from it. So we dequeue the A. Get A's left and enqueue it. Get A's right, enqueue it. Print out A or whatever. And then repeat. Now we dequeue again, except this time we get B. We print out B or whatever. Then we take B's left, add it to the queue. B's right, add it to the queue. And then we're done. Then we dequeue. Well, the next thing in the queue is C, so we get the C out. We print it out. We add its left, F. We add its right, G, and so on. That's it. So if we go look at the code, what do we have? We create a queue, level order queue. I've got a current reference for a node. I enqueue the start. Well, the queue is not empty. Dequeue. Here I'm adding to the sequence. This is like, think this is like I'm printing out. Print out the data. If its left is not null, add it to the queue. If its right's not null, add it to the queue. Repeat. That's all it is. So here's a handy place where a queue comes in handy. Now, it's kind of neat though, because you may have noticed, like with the recursive one, and remember, recursion and stacks go hand in hand. You'll notice that, I mean, even with pre, post, or in order, like the traversal goes all the way down to a leaf and then works its way back up, right? So it goes deep first. Where with the level order, it doesn't. But a level order is not using a queue, or is not using a stack, it's using a queue. And with the level order, it doesn't go deep first. It goes wide. It goes like through its breadth. So A, B, C, D, E, F, G, where the other ones kind of they go straight for a beeline to the end of one thing and then it backtracks. Where this doesn't need to backtrack, it just kind of like spreads out, which is neat. So stacks, you know, we'll sometimes call these, well, it's doing like a depth first search. And this would be more of a breadth first search. But that's just an observation. Okay, iterative pre, in, and post order is, well, with the iterative level order traversal, we used a queue. What do you think would happen if we basically took this and replaced it with a stack data structure? So it's not recursive, but we just do it with a stack. What do you think we would get? In the context of what we're talking about, this should be an easy answer. All right, well, that's okay. If we replace the queue with a stack, we'll effectively get, I mean, with the way this one is written here, we would get a preorder. We deal with the data, then we go left, then we go right. Then, and that's basically it. The only thing I would do is maybe I would move this. Okay, now I've got in order, if it was a stack. Or I can move it down here, and now it's post order, again, if it's a stack. So that's kind of neat. So the traversal analysis. Okay. Everyone raise your hand if you're paying attention. Luke's hand is still up. Okay, you're all paying attention. Good. I need you to focus. Because, listen to me. When it comes to computational complexity, it can be easy to give a knee-jerk response. Slow down and think about what I'm asking and think about what the data is. All right. Consider a binary tree with n nodes. So there are n nodes in here. I mean, in this example, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes. But consider it some arbitrary number of nodes, n. What is the computational complexity of the traversals? They're all going to be the same. How much work is there to do a traversal over a tree with n nodes in it? N. Any other guesses? Put your answer in the chat. We can't just have R2T2 answering here. Okay, 2, 2. Okay, the correct answer is n. Very good. Very, very, very good. If there's n nodes in there and you're visiting each one, how many do you have to look at? N. Now you might be saying, okay, that seemed really obvious. Why was he yelling at us? And here's why I was yelling. Do not forget the relationship between the number of nodes in a tree and the height of a tree. If I asked you the question, I have a tree, a binary tree of height h, okay, or depth, whatever. So its height is h, okay? What is the computational complexity of a traversal on a tree with height h? I'll give you a hint. H is not correct. Remember what the relationship between the height of a binary tree is and the number of nodes in the binary tree? Yes. No, it's 2 to the h. You were all kind of, you had the ideas. It's 2 to the power of h. Not 2h, 2 to the power of h. Yes. Because remember, the amount of nodes double every time. So you take h times, or 2 times 2 times 2, however many h's there are. And remember, there's that like, okay, well, it's like h minus 1 to the power of h minus 1 plus 1, or whatever. Okay, those are, remember, we're lazy computer scientists, so we care about asymptotic complexity. So I'd be like, oh, it's exponential, 2 to the h. But the reason it's 2 to the h is remember the relationship between the height of the tree and the number of nodes in the tree. And we were actually talking about this when talking about the binary search. Even though a binary search wasn't a tree, we could think of the data represented as a tree, right? So remember, this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 things in there. And there's the relationship between the height, how many levels we've got, or, well, levels minus 1, because this is level 0. There's the relationship between, the height and the number of nodes. So if the number of nodes you have to look at, like when you're doing a traversal, the answer is like, well, if you're doing a traversal where you have to look at so many nodes, it's how many nodes do you have to look at? But when I gave you the height of the tree h, I didn't tell you how many nodes there are. I told you what the height is, and well, we are learning that the height and the number of nodes have that relationship, that exponential / logarithmic relationship. The reason I say / logarithmic is, well, if I said there's n nodes, and I say, well, what's the height of the tree with n nodes? You'd be like, well, log base 2 of n. Because that log base 2 is the inverse operation of 2 to the power of. Let me prove that to you. 2 to the power of 24 is a big number. But if I do log base 2 of 2 to the 24, it's just 24. It just undoes itself. Right? So these are inverse operations, kind of like how like multiplication and divide and addition and subtraction. They're inverses. Where in the course material is that again? I can't find it. In the binary search stuff, but we're going to be talking about this a lot. Okay, and oh, look, right here. Intuitively, they're all n since we need to visit each node once and only once. If I change the question slightly to consider the tree with height h, what's the computational complexity? Well, 2 to the h. Why? Well, consider the relationship between the height of the binary tree and the number of nodes in the tree. And if you're left going like, oh shoot, where's the reference to this? Just draw one. Draw one and see, be like, oh look, if it has this height, this is how many nodes can be in there. And if it's this height, this is how many nodes can be in there. Like if we go back to previous. If we go and look at this example here, there's 1, 2, 3, 4, 5, 6, 7, 8 numbers on that last row, that last level. If I were to add another level though and completely fill it in, how many numbers would be on that last level? There are 8 on this one. How many would be in the next? 16. Very good. And then how many would come after that? How about after that? More. After 64, 120. Exactly. So you got the idea. Yes. So it's that like, that's the exponential. You're doubling every time. And if you're thinking doubling, remember. A lot of people actually, I hate to tell you this, chances are a lot of you had some really terrible high school math teachers. Okay, I hate to tell you, 2048, yeah. Yeah. I can also multiply by 2, that's good. You should have said I too can multiply by 2, but you missed a boat there, elongated. So, remember something here. I want to emphasize something. If I were to ask you, let's go back to paint. Some of you might be like, yeah, no crap to what I'm about to talk about. But I just want to make sure this is abundantly clear. I'll leave it like this so I can see the chat, just in case some questions come up. But I want you all paying attention and participating so we can move through this. If I say, the basic unit of arithmetic is counting, okay? Counting is all we have. Let's pretend we don't know what addition is, we don't know what multiplication is or anything else. I just can count, okay? So if I want to count, if I have the number 5, and like, I can add 1, I can count 6, 7, and I want to count 5 more times, that would get, okay, 5 to 6, 7, 8, 9, 10. Great. But I had to like add 1 5 times. Now, of course, we have generalized this idea of counting into addition. So what I mean is, instead of saying add 1 5 times, instead of counting 5 times, just do, here, look, we've got a shorthand for that. That's 5 plus 5. What does that mean? Well, 5 plus 5 more, that's 10. So addition is like a shorthand for multiple counts, right? Do you agree? Say you agree. Help me out here. You agree. You disagree. Well, I'm sorry, elongated. I can't help. If you can't follow this, I don't know if I can help you out. So, similarly, subtraction is the same thing, but we're adding by negative 1s, okay? So subtraction, same idea. And by inverse operation, I mean, if I had 5, I added 5, and then I did the inverse operation, I'm left with the original, right? I'm left with, well, like these cancel each other out. So, counting, that's great. But let's say I'm like adding by 5s, and I want to add by 5 times. So 5 plus 5 plus 5 plus 5 plus 5, right? And well, that's awesome. That's just, that's 25. Whoop, 5, right? We all agree with this. So we can add multiple, there's nothing stopping us from doing subsequent additions. But of course, humans are lazy, and this is a lot of writing, so we came up with a shorthand for describing multiple additions. And this shorthand is multiplication. If we want to do 5 plus 5 5 times, well, I would just say, okay, well, that's the same as 5 times 5, right? 5 times 5, well, that's just 25, right? So this multiplication is just like, it's like a generalization of the addition. Just do a bunch of these additions. How many times? 5 times. Do you agree with this statement? And division, of course, is the inverse. If I did 5 times 5, then I did divided by 5, well, these cancel each other out. Like a loop? Well, yeah, actually it is like a loop, but remember, it's just, what's this? Interesting. I appear to be zoomed in. Tell me what 5 times 5 is. Now reverse a linked list. What? I'm not sure what you're getting at there. So, great. So now we know that, like, okay, counting, we can generalize to just addition. And then addition, we can generalize to multiplication, right? Because multiplication is just multiple additions. So now let's say, if I just did 5 times 5, 5 times 5, right? Well, that's 25. But let's say I wanted to do multiplication multiple times. So I'm doing 5 times 5, 5 times 5 times 5 times 5 times 5. I'll just do this to 4, okay? So this is now like multiple multiplications. 5 times 5 is 25 times 5 is 125 times 5 is, I don't know, 600 and, I don't know. Someone do that for me because I can't do that in my head on Friday afternoon. 600 and something? 625? Come on, someone help me out here. You're taking too long to help. Seriously. 5 times 5 times 5 times 5. It was 625. I was right. Hey, points for me. 625. Great. But again, you may have found a pattern. Okay, multiple counts is addition. Multiple additions is multiplication. Multiple multiplications is what? Oh, well, look. This is just 5 to the power of 4. So this exponential is just multiple multiplications. And then, of course, the inverse of this is the log base of whatever the power is. No, of whatever the base is. Yeah. So log base 5 of 5 to the 4 is, 4? 2 to the, is 4. 4? All right, well, now I'm really embarrassing myself. But the point I'm making is, if you're scared of, log and exponential, those are weird. No, it's just this, it's the exact same pattern you've been following. It's just you've had bad math teachers that haven't really pointed out that it's just this subsequent generalizations. So, whatever. It's all addition. It's all counting. Just we got fancy at it and started skipping some steps. All right, back to business here. Okay, next. Let's talk about actually implementing this binary tree. So, a binary tree. What do we want to do with a binary tree? Well, maybe we want to check if a given element exists in a tree, check if a tree is empty, get the size of the tree, how many elements are in there in total. Traversals of a tree, maybe, add an element, but where? Remove an element, which one, from where? Okay, these are kind of trickier to answer, but, in general, we've got some stuff we want to maybe do with a binary tree. Yeah, with add and remove, what we want / want, what we want / what it means. Oh, okay. What we want / what it means will depend on the type of binary tree. So adding and removing something to a stack in queue was more straightforward. You always added to the same place. You always removed from the same place. With a tree, well, as you can see, it's complicated, right? So we'll revisit adding and removing. But similar to a bag, we know we want to add and remove stuff from our tree, but what exactly add and remove means will depend on the specific type of tree. Like how there was the sorted bag and the indexed bag. What add and remove meant depended on the specific type of bag. It'll be the same idea here with a binary tree. I'll give you a spoiler. We're only going to implement one type of binary tree. It's going to be called a binary search tree. That has a remarkable amount in common with binary search, but we're only going to implement the one. But for now, we're talking about binary tree very general. How it doesn't necessarily need to be a binary search tree. So if we make an interface for our binary search tree, here's what it could be. Add, remove, get root element, because why not? Contains, it's a Boolean, is empty, Boolean size, the size. We've got our toString down there, that's good. And then we've got a bunch of like iterators. And like, sure, we've got our iterator, but we actually have 4 other iterators. And that's the 4 for the different traversals. The 4 for the, well, okay, iterator. But how do you want to iterate? Where do you want to start? What order do you do the things in? Again, with a very linear data structure, there was no question. It was iterator. You start at the beginning, go to the end. And maybe you wanted to get fancy where you start at the end and you go to the beginning. That's as crazy as you can get. You could have made an iterator that starts at the middle, goes to the end, and then you go somewhere between the beginning and then the middle. That'd be a terrible idea. It's not very natural. But in general, the linear collections, you don't need fancy iterators. But with these nonlinear collections, iterator, how? There's a lot of valid popular options. So we'll implement an iterator for each of these because. So any questions about this interface? And here, I'll open up the binary tree interface. Add, remove, get root element, contains, is empty, size, iterator, another iterator, another iterator, another iterator, another iterator, and toString. Yeah. That's it. That's what we want to do with our standard bag, notwithstanding anything that comes with the specific implementation of the binary tree. I said bag, I meant binary tree. But yeah. So now when it comes to the implementation, well, we're going to talk about a linked implementation because this is probably a little simpler for us. We could do an array one. There's nothing stopping us. You totally could. But we're going to do a linked implementation. So we're not going to implement a binary tree. It will be inherited for when we make a binary search tree, which is the next topic. But one way to implement a binary tree is with a collection of linked nodes. So like a linked queue, like a linked stack, like a linked whatever, we're going to do that same idea, except now we've got left and right. So instead of like next, it's left and right. So we'll make a binary tree node that is nearly identical to the regular old node we've seen. It's got data and it's got a next, except it's got data and then, well, it has 2 nexts, left and right. That's all we need. So if we go look at the binary tree, binary node, let's have a look-see. What do we have? Binary node, data, binary node left, binary node right. Constructor, you give it data and whatever, it's got nothing. Get data, return data, set data, get left, get right, set right. That's all. So obviously this is more complex than just the regular old node, because the regular old node just had a next, where here we have left and right. But other than that, it's just the getters and the setters. Get data, get next, set next. That's all. So it is with these binary nodes that we can create trees. Oh, okay, yeah, I've got it here. Yeah, there's your binary node. Linked binary tree. Okay, although there is no implementation of a general binary tree, we can discuss what some specific tree-based algorithm. We can discuss what some specific tree-based algorithms. This is an issue. Someone can make a PR for this because that's an incomplete sentence. I hear a question. Is it like a node with 2 nexts? Exactly, except they're called left and right. That's all. That's it. That's all it is. That's it. And remember, like, okay, well, which one's left and which one right matters. But I guess it always mattered which one was next because, you know, it's there. So how could we go and implement something like a size function or method? Well, how about this? Okay, so first of all, we'll have our public size. Again, this is for a this will be true for whatever, for a binary tree. So this will also be the case for binary search tree. And if we go and I open up my binary search tree implementation, no, that's the linked binary search tree. And we look for size. It's in here somewhere. Yeah. Size. Oh, no, I stored the size. Shoot. All right, well, I spoiled my own fun there. All right, well, either way, we'll talk about the algorithm. I have a binary tree, and I have access to the root node. So what's the size of the tree? Well, we can go count every element. So how about this? If the current node doesn't exist, well, the size of that tree is 0. If it does exist, well, then the size of this tree is 1 plus the size of my left tree and the size of my right tree. Now, I don't know how big the size of my left tree is or the size of my right tree is, but the good news is I'll just make a recursive call to those subtrees and ask their roots. Now, if they don't exist, they'll return 0. If they do exist, they'll return 1 plus whatever the size of their left and right subtrees are. I don't know about you. This is awesome. Look how elegant and simple this is. Size. So we have our public method here that just sets it up, because if I ask the size of a general tree, I don't want to have to specify, okay, you start at the beginning, right? So this size we'll call the first recursive level, where this one calls it with root, and this is the general recursive one that has some arbitrary current, but it starts at root. So if current is null, its size is 0. Otherwise, it's 1 plus however big the left is and however big the right is. That's it. Isn't that glorious? That is magical. That is so simple. And its simplicity is caused by this beautiful elegance of recursion here. If I were to do this iteratively, it'd be a lot more annoying. This, though, oh, this is nice. So what's the computational complexity? Well, I just have to count each node. And how many nodes are there? N. So it's order N. Where does current change? When I call size on current.getLeft, that's where it's changing. As I'm calling the size on current's left. So then in that call frame, when it calls that size again, current will be the previous current's next. Does that answer your question? And then, of course, also here. Now, if I were to ask you, though, so here's a little quiz. This line here, this one line of code actually has 2 recursive calls in it. 1, 2. Based on this, I mean, this is kind of a silly question to ask, but I'll ask it anyways. Is this a pre, in, or post order setup? It's kind of a silly question, so if you don't have an answer, that's fine. But I want to see what you say. Pre. Yeah, I'd say pre. It's the currents, the lefts, and then the rights. If I said size of the left plus 1 plus size of the right, that's in, I guess. But it doesn't really matter here. All right. So now let's talk about a contains. I want to search through my binary search tree to check if something exists in there. So let's see. Do I have my contains? Yes, I do. So here's my binary search trees one, except it's actually slightly better than the one I'm talking about here. So here is the contains. So I've got my public facing contains that just takes the needle, the thing I'm looking for. And then I have the private one that'll actually be the recursive one. And it says, okay, if current is null, obviously I haven't found needle, right? But if current's data equals the needle, then I found it. If I haven't found, if the tree exists and I haven't found it though, where is needle? Well, needle is either in the left subtree or in the right subtree, right? So just call contains on the left subtree looking for needle. And then call it on the right subtree looking for needle. You'll notice that this is the OR, and this is actually the short-circuited OR, meaning that if this ever returns true, it never has to evaluate the other half. But, yeah, contains. It's either the current thing I have, the current node either exists, has it, or doesn't have it. If it doesn't have it, then continue the search on the left subtree. If we ever finish the search on the left subtree and we don't find it, We'll then continue the search on the right subtree. If we finish the search on the right subtree and don't find it, well, then that thing's not in there. If you're struggling with this one and this one, I urge you to take your time maybe later going over this. And then the traversals, well, it's the same as what we were just talking about. So yeah, that's it for a binary tree. And you can download the binary tree interface. The next thing we're going to talk about is a binary search tree where I think, okay, we're going to talk about, there's a lot of details in it, and then we'll jump on to the implementation of the linked binary search tree, where we'll talk about some of the specifics. Some of these functions our methods get quite complex, so I'll warn you about that. And then after that, it's just the sorting stuff. I know these look long, but we've covered actually like all of this stuff we covered in 161. So it'll be a review. It's the second sorting that won't be as much review. All right, anyways, that's it for today. Do we have any questions before we wrap up today? All right, well, in that case, I will see you all. I'll see some of you on Monday, and if not, the rest of you, hopefully all 14 of you, on Tuesday. All right, have a good weekend.